Character table. What about character table? What was that? Cyclic groups, character tables in which we have imaginary characters. That is one thing, right? Are we all okay with that? What else did we learn? I just said imaginary. What is the real thing that we learned? How to reduce reducible representations into representations that are not reducible. Right? How to reduce reducible representations into representations that are not reducible. That is what we learned. How do we reduce reducible representations to irreducible representations? Yes? Block factorization. How do I do block factorization? But did we do similarity transformation? What we said is that if you want to do similarity transformation, that is the right thing to do. But it can become very complicated. So in case you have gone through that example that I suggested you to go through before mid-sem in Harrison Bertolucci, then you will understand how complicated it can become. It's extremely difficult to find the matrices that are actually supposed to be used to perform the similarity transformation. We took an easier way out. We said that if this is the reducible representation, rather if this is the reducible representation gamma, then and if it is written as sum over j aj gamma j, what is gamma j? J is the gamma j is the jth irreducible representation which makes up the reducible representation. Earlier we had studied that you can construct a reducible representation by block addition of the irreducible representations, right? Isn't it? So this is how I can write it. So if this is the case, what we said is that chi of r will be equal to sum over j aj chi j of r, and hence what we found was ai is equal to 1 by h sum over I is a specific number, it cannot be sum over I, sum over r, chi of r, chi I of r. This is how we break up reducible representations into their constituent irreducible representations. All right? Okay? And this is a golden rule. I need you to remember this. So today what we are going to do is, we are going to generate a reducible representation to start with. So what we will do is, we will generate a reducible representation, and this reducible representation is going to be something that is relevant to chemistry, and then we will see how we break it down into its components. So now we are really getting into applications of all these things that we are studying so far. I had actually planned to do it at the end, but then for different reasons I thought I will do it now, because then something that is very easy, and then it is something that can give you a lot of food for thought, and I can give homework assignments which you can solve over the next couple of weeks. Yeah? So this is what we are going to learn today then, determination of the symmetries of normal modes of vibration. What is the meaning of normal modes of vibration? I think we have discussed that in this class. What is the meaning of normal modes of vibration? Linearly independent ways of vibration. Mode means way, normal means you already know what is the meaning of normal, right? The independent. So you can write this set of vibrations, and you can say that this set of vibrations are linearly independent. And for water, we already know what are the normal modes of vibration. I think we worked that out, right? And I think we also, what we did was, we found the symmetry classification of those normal modes of water, isn't it? So total the symmetric stretch, to which symmetry species does it belong? A1. What about the asymmetric stretch? B1. And what about the bend? A1. So you know how to perform the symmetry classification of normal modes of water at least, right. Now, I think you will agree with me if I say that we can do it fairly easily, right. We did it quite simply, right, in a matter of few minutes just before mid-sem. So water, it was simple. However, if you just add water, how many atoms are there in water? 3. If you make it a 4 atom system, and of course you can make it a 4 atom system in 2 different ways, right. You can generate a TD group, or you can generate, what is this group? Say BF3 or carbonate. It is D3H, right, because you have D3 perpendicular to the plane of the molecule, right. Each of these bonds is a C2, molecular plane is a plane which is horizontal, so it is D3H. For D3H molecule, what I am showing you now is the normal modes of vibration. Are they simple? Can you guess what they will look like if I do not tell you? This one you might be able to guess. So this is like symmetric stretch, it is just that there is another bond, so that is also stretching. Even this you might be able to guess. What is this kind of motion? It is doming motion. Doming motion, dome, you know dome. You go to hostel 15, this thing, mess hall, there is a dome on top. Of course, there is no reason why you have to go to hostel 15. There is a dome on top. Or if you see many buildings in Hiranandani, they have this dome on top. So this is doming motion, right? So it is like this. So I think this is easier than that. This is the molecule, isn't it? Carbonate or BF3, whatever it is. What is the third one? I cannot even see it. Okay. Can you see all 3? Right? So doming motion would be like this. All 3 go out of plane, then come back, and all 3 come behind the plane also. Understand what is doming motion? Actually, it is a planar molecule. If it goes out of plane, then you get what is doming motion. Okay, what about this bond going that way and these bonds coming this way? Is that in normal mode of vibration? This bond going this way and these bonds coming this way, it is actually vibration plus rotation. It is like the molecule is rotating. Okay. So all 3 going one way symmetrically. This is plus phase and this is minus phase. This is doming motion. Okay. Understood, Jaladhar?
Yes, but that kind of symmetry will change.
Symmetry will change, but then don't forget we are talking about simple harmonic oscillation. What is an essential condition for simple harmonic oscillation? This is a very, very good question. No, not coming back to the same position. I have something else in mind. Good. So this one perhaps you can, so you understand the meaning of this plus and minus, right? It does not mean that this is 3 plus charge and this is 1 minus charge. This one is going behind the plane, the central atom. The other 3 atoms are coming above the plane. And those who have studied CH442, either with me or with Arindam, for them this is a repetition, this class, but then Vibha studied it long ago when he was much younger. So it's good that he is studying it again. And those who have studied it this year, they have not come. So it's okay. But now, so you can guess this maybe. With a little effort, you might be able to guess this also. But then when it is bending, see here it is bending, here also it is bending. What is the difference? The difference is that this atom is fixed and the central atom is moving, and in this case both the atoms are moving. So even if you can guess that this bending motion will be there, it is not very easy to guess whether the outer atom will move or whether the central atom will move. And if you can actually guess these, this and this one, then we should interchange places. Can you guess this? I tell you, sketch the normal modes of BF3, will you be able to draw these arrows like this? This in this particular angle, that in that particular angle? Not easy. I cannot guess this if I do not know anything else. So the problem is just increasing one atom makes it so complicated. So if you want to talk about symmetry of normal mode of big molecules, how do we do it? We cannot guess, unlike water. We need something else, and that is where symmetry itself helps us out. That is what we learned today. Okay, that is where character table comes very, very handy. Your mobile phone inside your pocket. It's impossible. You cannot work with larger molecules by intuition. It's impossible, just impossible. Right? So what do? You need a recipe. Once again, we like recipes, we love recipes. Right? Now it is time for one more recipe. Now, how many normal modes would an n-atomic molecule have? If it is linear, then it is 3n minus 5. If it is non-linear, there is 3n minus 6. What is so, where did 3n come from? Number of degrees of motion. No, wait, yeah. Vibration translation is fine. Where did 3n come from? You tell me that first. Total number of degrees of freedom is 3n, right? What is the meaning of total number of degrees of freedom? No. That is also, those are also degrees of freedom. But how did you get 3n? That is what I am asking. I have an n-atomic molecule. Why do I say that it must have 3n number of degrees of freedom? Once again, easier than what you are thinking. Yeah, x, y, z. Each atom can go in x, y, z direction, right? Now, when all the atoms move the same distance along x, same distance along y, same distance along z, then it is translation. Otherwise, it is rotation or vibration, isn't it? That's all. So, your starting point even in this 3n minus 6 is the x, y and z axis attached to each and every atom. You understand that? So, what we do is you can start with 3n number of Cartesian coordinates, 3 for each of the n atoms. Okay with that? Then what will I do? Then I am going to eliminate the translation and rotational coordinates. It is very easy to do that from the character table, because you already know where x, y, z belong, where rx, ry, rz belong. And then transformation to symmetry coordinates is something that we are not going to do, but we will at least talk about, you know already, right, that you know everybody has studied IR spectroscopy at some level or the other. So, if in a carbonyl molecule, what is that 1700 band? So, how do we do that? How do we say that that is because of carbonyl and something else is because of CF or whatever? We will learn a little bit of that. So, you start with 3n Cartesian coordinates, build a reducible representation, then decompose it. Okay, so here goes. This is my molecule. I have just given it 4 numbers instead of writing the atoms. It is a little more convenient. Okay, so if it is BF3, then this atom number 4 is B, 1, 2, 3 are F. If it is carbonate, then atom number 4 is C, 1, 2, 3 are O. Okay, now what do I need to do? I need to draw the X, Y and Z axis on them. I will draw them like this. You can draw in any way you want, does not matter. Okay. This discussion today is entirely from Cotton's book. Okay, Cotton's book on symmetry. It's clear enough, isn't it? Yeah. So what have I drawn? I have drawn x1 along this bond, so it's basically pointing downwards. Y1 perpendicular to it. Z1 is pointing towards us. Okay. So everybody is clear about x1, y1, z1, x2, y2, z2, x3, y3, z3, and x4, y4, z4. Right? Okay. Now what we will do is, we are going to see how these coordinates move. So what are basically what we have taken is, we have taken unit vectors along x, y and z for every atom. They are all unit vectors, remember that. We will see how they transform. If I now want to make a representation out of this, suppose I want to make a basis out of this. Unfortunately, people who ask those relevant questions are not here today. What to do? They can watch the video. If I want to make a basis out of these x's and y's and z's, then what will be the dimensionality of that basis? 12. No? 12. 12. So now if using that, if I try to make a representation, how will we make the representation? We are going to work out the transformation coordinates. If I make the representations using that, what will be the dimensionality of that reducible representation? 12, right? For D3H, what are the symmetry elements that are there, symmetry operations that are there? E, C3, and how many operations for C3? C3 square, then S3. Less than 12, right? Let me show you the character table, then it will be a little easier. Yes, of course. You cannot deny S3 its square. See D3H? What do you have? You have E, 2C3, 2C3 means C3 and C3 square. Then you have 3C2, 3C2s you can see easily along the bonds. Then you have sigma H, how many sigma H? 1. Then you have 2S3 similarly, and you have 3 sigma V's. What is the total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So this is a case where H is 12 and we are working with a representation which is also of the same order. Okay. Will I have to write something or do I need the character table first? I think I need the character table first. Yes. So let us leave this in this Zoom lab. So E is very easy. What will be the matrix for E? You should understand what we are doing, right? What will be the dimensionality of the matrices now? So we are going to write down now 12 by 12 matrices, and Dola is not at all amused at that prospect. But as we will see, things will take care of themselves. Just wait and see. What will be the E matrix? 1 0 0 0 0 0 and all that, 0 1 0 0 etc etc, 0 0 1 etc etc. What will be the character? 12. Now that is easy. Now and see, we worked out one matrix already. Next, what do we have? We have C3, and for C3 we don't have to bother about C3 and C3 square separately. Just C3 is good enough, because after all C3 and C3 square belong to the same class, so character will be the same. Alright. So what will happen if I apply C3? What will happen to say Z4? Z4 will remain Z4. What about X4 and Y4? They will be turned by 120 degrees. And then we know what the relationship it will be, because we already worked this out earlier, isn't it? 120 degree rotation. Now what about say X1, Y1, Z1?
Y1 will become X2.
Yes. Y1 will become X2? No. Z1 will become Z2. See, don't forget that this X1 is along the bond, right? So when you are rotating transformed X1, X1 dash will also be along this bond. So it will be a vector sum of X2 and Y2. Isn't it? So let's just draw this. This is what it will be. This is where you started from? So just remember this, Z1 is very easy. These are the Zs, right? So Z1 becomes Z2, Z2 becomes Z3, that's not a problem. Now, then next it's easy to see X1. X1 is along the bond. So X1 dash will be along this bond. Moreover, all the other X's will be parallel to X1. Isn't it? The other way of thinking is that this X4 is going to be rotated by 120 degrees. So if X4 is rotated by 120 degrees, where will it go? A little bit of high school geometry once again. Won't it be like this? So forget everything else, look at X4 dashed and X1 dashed, right? They are along this bond, and then you can just confidently draw X2 dash parallel to X1 dash and X4 dash, draw X3 dash parallel to X1 dash and X2 dash. Alright, these Z's are very easy. z dashed. What about y? How do I draw y? Y also is very easy, because y has to be perpendicular to x, right. So, it is very easy for me to draw y1 dash perpendicular to x1 dash, y4 dash perpendicular to x4 dash, and the check is that the y's should be parallel to each other. So, now you see y4 dashed here is parallel to y1 dashed here. Then similarly you can draw y2 dashed here and you can draw y3 dashed here, alright. So, I have now rotated the molecule and I have rotated the coordinates as well. Now, let me, without getting scared, let me construct that 12 by 12 matrix. What is easiest out of x, y and z? Z. So, let me see what is z1 dashed. Z1 dashed is equal to, in original coordinates, Z2, isn't it? Z1 dashed equal to Z2, will you agree with me? What is Z2 dashed? Z3. Z3 dashed is Z1, Z4 dashed is the easiest, Z4, right? Okay, very easy. Even the other one is easy because we have already worked it out so many times, isn't it? So, we will write it like this. What is x4 dashed? Okay, well, since we want to start with one, let us do it like this, just zooming in a little bit. So, this is x1 dashed, y1 dashed, and it will be easier if I draw the original coordinates also there, x2 and minus y2, isn't it? x2 and minus y2, isn't it? This direction is minus y2, right or wrong? So, now what will be the angles between, say, x1 dashed and minus y2, x2 and y1 dashed? What will these angles be? These will be the angles. Angle between x1 dashed and minus y2 is 30 degrees. That between x2 and y1 dashed is also 30 degrees, and that between y1 dashed and minus y2 is 60 degrees. So, now you can write, you have already done this. So, tell me what is x1 dashed? Minus half x2 minus root 3 by 2 y2. Have you done this earlier or not? You have done it, right? It is very easy. What happened? Okay. What is y1 dashed? Root 3 by 2 x2 minus half y2. Alright, convinced? Convinced? Similarly, x2 dashed will be minus half x3 minus root 3 by 2 y3. y2 dashed will be root 3 by 2 x3 minus half y3. x3 dashed y3 dash you can write x4 dash y4 dash also. Are you all okay with this? Huh? But we are going a little fast, so please work it out yourself also. Okay. Now, are you all okay with this? Huh? Now, what do I want to do now? I want to write this in matrix form. To do that, first let me get rid of the figure, then let me write the equations of 1, 2, 3 and 4 together, and if I want to write it as matrix, I have to put in all those terms where coefficients are zeros, right? Most of the terms have coefficient of 0, right? But I have to write it. So, let me do that. x1 dashed equal to 0 x1 plus 0 y1 plus 0 z1 minus half x2 minus root 3 by 2 y2 plus 0 into z2 plus 0 into x3, and I am tired, 0 into everything else. It's so nice, the computer knows what I want, it writes it itself. Alright, is this okay? Huh? Similarly, I can write it for y1 dashed and z1 dashed and everything else. The computer is really smart. Okay, these are the matrix equations. Do you see the non-zero blocks? These are the non-zero blocks. Okay. All right, these are the non-zero blocks. Anybody want to say anything at this point? Now, it is very easy for you to write this equation in matrix form. Huh? This is the equation in the matrix form. Non-zero blocks are still in blue. Okay. These were the linear equations. Now I have written them in matrix form, that's all. Alright? Huh? You just have to believe me that I did not cunningly change some number somewhere, and you can verify when I send you the slides this evening. Now what do I want? I have worked out the transformation matrix. I have worked out the transformation matrix. It was not all that difficult. 12 by 12, it was easy. It will get easier after this. But before that, tell me what is the character, what do I add? We add this, the trace, very difficult addition, and answer comes to 0. Like many things in physical chemistry. So here chi turns out to be 0, right? Chi of C3 equal to 0. Now, what is the important lesson that we have learned in all this exercise? We have learned that a rolling stone gathers no moss. What do the non-zero blocks stand for? The blue blocks? They stand for the contribution of the original coordinates in transform coordinates, right? So now, what has happened here? As a result of application of C3, atom 1, what are the atoms that change places? You will remember 1, 2 and 3 change places, 4 did not change place. So what has happened is that the non-zero blocks have gone off diagonal for 1 and 2 and 3, because x1 dash, y1 dash, z1 dash are completely expressed in terms of x2, y2, z2. x2 dash, y2 dash, z2 dash are completely expressed in terms of x3, y3, z3. And similarly, those in for atom 3 are completely expressed in those of in the coordinates of in terms of coordinates of atom 1. No? And since they have gone off diagonal, they cannot contribute to the value of the chi. The only atom that contributes to chi is C4, which has not moved. So you have learned that a rolling stone gathers no moss. Understood? So have we all learned, do we now all believe in this ancient wisdom that a rolling stone gathers no moss? Huh? So off diagonal blocks do not contribute to chi, and that simplifies our life very much. For all subsequent operations, what we will do is we are only going to focus on those atoms which do not change places. Okay? And that is how we are going to cheat, and we are going to work out these big matrices without really working them out. And if you thought that is the end of the story, it is not. So, picture baki hai thoda bahut. We will come to that a little later.